Assalamu alaikum dear students. I welcome you to 34th lecture of probability and stochastic processes. In the last lecture we started our discussion of Markov chains, which are a special class of stochastic processes, a special class of discrete time or discrete parameter stochastic processes. In this class we have a collection of random variables with an associated precedence, with an associated sense of time. If there is a random variable, then the other random variables either happen after this random variable or before this random variable. So all these random variables are associated with an instance of time at which they are observed or they realize their values. And in Markov chains, the relationship between different neighboring time-wise, neighboring random variables is a special one, and this relationship is characterized by the Markov property. I talked about Markov property in the last lecture. Let's have a look at the formula for the Markov property. The formula for Markov property is being shown on your screen, and the formula says that probability of capital X of n plus 1, the random variable x with index n plus 1, being equal to small x of n plus 1, given that the other random variables in the collection xn, xn minus 1 and so on having values shown here, that is xn being equal to small xn, capital X n minus 1 being equal to small x n minus 1, so on, and last random variable in the collection capital X0 being equal to small x0 is equal to probability of capital X of n plus 1 being equal to small x of n plus 1, given that capital Xn is equal to small xn. This long complicated equation could be confusing to you, but if you think about it, all it is saying is that if you know this state of all the other random variables which are previous to this capital X n plus 1, only this is important. This equation, by the way, is not saying that value of xn plus 1 does not depend on capital X0, x1, x2, x3. It does. Think about that gambling situation. So capital X3 is your net holdings at third time instance after 3 games have been played, and capital X4 was your net possessions after 4 games have been played. So this equation is not saying that probability of your possessions, your net holdings for 10th timing instance when the 10 games have been played is not a function of your possessions after 5 games or 4 games. They are dependent on that. But if you are given what you have after 9 rounds of play, that's all you need to know. What you have after 9 rounds of play has all the information of what you had at 8th round, plus what happens from 8th to 9th round, and what happened from 7 to 8, 6 to 7, and so on. So capital X of n plus 1 does depend on all the variables, but the value of the immediately preceding random variable capital Xn captures all the history. Hence, probability of this random variable given all the history is equal to probability of this random variable being equal to small xn plus 1 given the value of the immediately preceding random variable. So Markov property lays out the rule for relationship and conditional probabilities between collection of random variables. The other thing that we discussed that we should have another look at is the procedure to find the one-step transition probability, what is the probability of capital X n plus 1 being in state 0 given some other pieces of information. This equation was used when we were deriving a general recursive formula to go from a certain random variable xn being in certain state to next random variable xn plus 1 being in a certain state. So this formula of probability of xn plus 1 being in 0 state is equal to this formula given. Why this formula works? What this formula represents? This formula represents what we already discussed in 5th lecture, that is partition of the sample space. That is the total probability of a random variable. If this is the probability in question, then this event which is being represented by this probability is being sampled through partition of a whole sampling space, and this represents the partition of the whole sampling space, the previous random variable having value either 0 or 1. These are the only two states that the previous random variable could be. Let's look at that slide which I have borrowed from lecture 5. This is the slide where the event A is shown with this round figure, and the whole sample space, the big rectangle, is partitioned into B1, B2, B3, three non-overlapping subsets of sample space. Then probability of A is equal to summation of probabilities of this A being intersected with these three B1, B2, B3, the partitions of the sample space. This idea is used in that equation where we used the concept of finding the probability of xn plus 1 being equal to a summation of two other pieces of information. So in this equation, this is our event A, xn being equal to 0 in state 0. And here this is combined with xn is equal to 0 or xn is equal to 1. So these two events, the previous random variable attaining a value 0 or previous random variable attaining a value 1, represents partitioning of the whole sample space, and this is combined in this manner, which is equivalent to intersecting the two events, and this is combined in this manner, and the probability of this event is summation of this joint probability and this joint probability. And these two joint probabilities are then again shown as multiplication of a simple probability and a conditional probability. Why is this so? All you have to do is break this conditional probability into its expression. So conditional probability of capital X n plus 1 being equal to 0, given that capital Xn is equal to 0, can be written as joint probability divided by the probability of conditioning event. This capital Xn is equal to 0. This cancels out with this one and you get your joint probability. So when you have this expression, you can represent these conditional probabilities as one-step transition probabilities, and those are well-known quantities for any Markov chain. So this formula uses the concept of partitioning of sample space and the relationship between joint probability and the conditional probability to get an expression which we derived in last lecture, which related probability of capital X n plus 1 being in state 0 in terms of probability of previous random variable xn is equal to 0 and the transition probability from xn is equal to 0 to xn plus 1 being equal to 0, plus probability of previous random variable xn being equal to 1 multiplied by the transition probability of previous random variable xn being 1 and going to the next random variable equal to 0. So analysis of Markov chains relies heavily on the fact that probability of current random variable being in a certain state can be derived from probabilities of previous random variable being in all the states possible and multiplied with the transition probabilities from each state of the previous random variable to the current random variable being the state that we are interested in. In last lecture, we analyzed thoroughly example of a Markov chain representing a device which has a tendency to break down, but once it breaks down, it gets repaired by the next day. So you observe the state of the device from day to day. So your instances of sampling, the instances in time when you look at the value of the random variable, you look at the state of the device goes from day to day. So if it is working this morning, it could be broken by next morning, but if it is broken this morning, it will definitely be repaired by next morning. So that simple example was analyzed and we got a general expression for the formula for the nth random variable, the state of this Markov chain at nth timing of observation to be a certain formula. Let's have a look at the formula again. The first formula says probability of xn being in zero state is equal to p over 1 plus p plus minus p whole raised to power n multiplied by this expression in square brackets. You might have noticed one change in this formula. In last lecture, I wrote pi and then state 0, and similarly pi and then state 1. Now I have used more traditional notation of introducing a subscript 0 here next to pi. This represents the probability at timing instance 0. So first random variable, the starting random variable, the probability of that random variable being in state 0 or state 1 is indicated here. We are going to use this notation because pi 1 of 0 will be the probability of random variable x1 being equal to 0. So this 0 represents the initial probability. The other formula is probability of xn being in state 1, and the formula is very similar except this change that wherever there was p we have 1, and instead of this initial probability of being in 0 state we have replaced initial probability of being in state 1. So these two formulas represents this simple Markov chain being in state 0 or state 1 at the sampling instance n. If you carefully look at these two formulas, they give you a lot of information. Suppose p was 1. If p was 1, then if machine was working at a certain morning, it will definitely be broken by the next morning. And when it is broken on that next morning, the day after that, it's definitely going to be working. So if p was also equal to 1, then this Markov chain would keep on jumping from state 0 to state 1 to state 0 to state 1, and it will not be working for 2 consecutive days. If we put a value of p equal to 1 here, you will get much simplified expressions and they will represent this situation. Let's have a value of p which is very small, which represents that this machine is very reliable. If p is a very small number, then this probability of machine being in working condition day after day is very close to 1. So it is very rare occasions that this machine breaks down, comes here, but immediately becomes in working order again. So if p is a very small number, you can look at these expressions and you can see that this number is going to be a very small number, p divided by 1 plus a small number, the same number, almost the same number. So probability of this random variable being in state 0 will be a small number, and probability of this random variable being in state 1 will be a large number, close to 1. 1 over 1 plus a small number is a number slightly smaller than 1. Hence, probability of this Markov chain being in state 1 is going to be a larger number. And we talked about asymptotic behavior in the last lecture. So if you look at the asymptotic behavior and p is a number less than 1, then this expression vanishes. This whole expression vanishes because this number is going to approach 0. So is going to happen to this expression. Hence, asymptotically, probabilities will be p over 1 plus p and 1 over 1 plus p. Once again, if p is a very small number, then asymptotically, this Markov chain will be found in this state with much higher probability than in this state, which represents that machine is broken. In last lecture, I gave you a homework. I asked you to analyze the behavior of the Markov chain, which represents a similar device or machine, but probability of it getting repaired the next day was less than 1. It was possible for the machine to be not getting repaired in one day, and it can take multiple days. I also talked about the technicians having zero memory of what they did on the previous day, so that it follows the Markov property. If you are in a certain state, you don't try to remember how you reached there. So we are going to just see the formulas for that case and try to make sense out of those formulas. This is the Markov chain where if machine is broken, it gets repaired with the probability q, and it does not get repaired in one day with probability 1 minus q. Similarly, if it is in a working order, it breaks down with a probability p, and it keeps on working till next day with a probability 1 minus p. The formulas for this Markov chain being in state 0 or state 1 are shown here, which are supersets of the previous formulas. In previous formulas, q was 1. So in these formulas, if you just replace q with 1, you will get the previous formulas. Here particularly you can see that 1 minus q cancel each other out, and you get minus p whole raised to power n. So if you look at these formulas and try to see the asymptotic behavior under regular conditions, that is p and q both are numbers between 0 and 1. If they are between 0 and 1, then this whole quantity will be a number between a positive number slightly less than 1 and a negative number also with a magnitude less than 1. So in any case, if p and q are reasonable numbers between 0 and 1, this whole expression is going to either oscillatory manner or in a straight manner going towards 0. So asymptotically, these expressions to the right of these first expressions are going to vanish. Hence, asymptotically, probability of xn being in 0 state is p over p plus q, and probability of xn being in state 1 is q over p plus q. Let's look at this case where p and q are some numbers between 0 and 1 and they are equal. If they are equal, then these expressions are equal. So if probability of this machine breaking down or getting repaired in one day is same, then probability of you finding this Markov chain either state 0 or in state 1 is going to be same. You can have this machine to be a reliable machine, then p is going to be a small number, and you can also assume that your technicians are very capable, so probability of them repairing in one day is very high. So if you have p a small number, say 0.05, and q a large number, say 0.95, you will find out that this probability is very small and this probability is very large, meaning that probability of you finding this machine in state 1 is much larger than probability of this Markov chain being in state 0, that is this machine being broken down. So all these formulas should make sense to you. Try to think about the different parameters and the roles they play and how to asymptotically extend these formulas to see that in the long run the behavior of the machine is determined by these formulas. So far we have done detailed analysis of Markov chains with only two states, 0 and 1. In last lecture, we saw examples of Markov chains with many more states and quite complicated state transition scenarios. Let's extend our horizon and study a Markov chain with 3 states. This Markov chain represents a variation of this problem we were discussing, where a device fails, it breaks down, and then it gets repaired. Let's have a special repair scenario. So if the fault is minor, it gets repaired the next day by the local technicians. And if the fault is complicated, then this device, this machine, could be sent to the manufacturer in some other country or some other city. There, the technicians of the manufacturer are going to work on that, and they can repair it in one day, depending upon the difficulty of the fault and the difficulty in repairing that, or they can take more than 1 day. So if machine goes to the central repair facility in some other city or some other country, then it can take 2, 3, 4, 5 days to get repairs. And if it is repaired in the local facility, it gets repaired immediately and it is in working order the next day. Let's have a look at this Markov chain and its state transition. So this state 1 represents that machine is working. State 0 represents that it was sent to the local facility and they tried to repair it. If they repair it, they send it back, and probability of that happening is Q. And 1 minus Q is the probability that they failed to repair it in 1 day and they send it to the external facility, and there it either gets repaired and comes back to the working order, or it takes multiple days for this machine to get repaired. As you can see, we have used 1 and 0 same states, and here a state of label -1 is introduced. But it's not necessary. We can relabel these states. We can call this state 0, the external repair facility. State 1 is local repair facility. And state 2 is that machine is in working order. If you look at all these transition probabilities and transition scenarios from different states, this Markov chain is slightly more complicated than the Markov chains we have analyzed thoroughly. This has 3 states and many transitions from state to state. To analyze this Markov chain in greater detail, you once again have to find the probability of this state being in a certain value, given that it was in other values in the previous sampling instance, and then the transition probabilities. Let's look at all these transition probabilities in the light of these transition scenarios. The first probability, transition probability, is from state 0 to 2. It is that if it was sent to the external facility and it got repaired and came back. So this transition probability is from state 0 to 2, and it says clearly that the previous state was 0 and the next state is 1, and this is equal to R. As you can see, this is the transition, and probability of this transition from state 0 to 2 is R. The next transition probability is from 0 to 0. That is, it was sent to the external facility and it could not be repaired in 1 day. So by the next morning it was there in the same facility, and probability of that is 1 minus R. Here is your transition from 0 to 0 with corresponding probability of 1 minus R. The next transition probability is from state 1 to 2. That is, it was sent to the local repair facility and it got repaired the next day, and probability of that happening is Q. Here is your transition from 1 to 2 with probability Q. And there are other transitions, 1 to 0, 2 to 1, 2 to 2, with corresponding transition probabilities. So there are only 6 transitions, and there are other 3 transitions which are 0. For example, the Markov chain does not stay in state 1. If it is sent, the machine is sent to local facility, either they repair it by next morning or they send it to the external facility. They don't keep it. And there are other transitions which are absent. So there are a total of 6 non-zero transitions, and we can use these 6 non-zero transitions with other random variable to find formulas which tell us the probability of this Markov chain being in a certain state. Let's have a look at those formulas. Here is a general formula which tells us the probability of capital X n plus 1 being in state 0, and this is expressed as a sum of joint probabilities, sum of 3 joint probabilities, and this is again an application of total probability. This is event A, and all these 3 states combinedly represent the partition of sample space. The previous random variable xn could be in state 0, could be in state 1, and could be in state 2. These are the only 3 possible states for the previous random variable xn, and these 3 states represents complete partitioning of sample space, and they are combined with the formula of probability xn plus 1 being 0, and you get summation of 3 quantities. And then these joint probabilities are represented as multiplication of this probability of previous random variable being in a certain state and the transition probability, the conditional probability, which is from 0 to 0, you see it here, from 1 to 0, you see it here, and from 2 to 0, which you see at the last line. So this formula of probability of xn plus 1 being in state 0 is changed to this formula, that probability of xn being in state 0 multiplied by transition probability from 0 to 0 plus probability of previous random variable being in state 1 and then transition from 1 to 0 plus probability of previous random variable being in state 2 multiplied by transition probability from 2 to 0. If you look carefully and compare this formula with a similar formula for the case of two-state Markov chain, you can see that it was easy for us to replace one of these probabilities, that probability of xn being equal to 0, with 1 minus probability of this one being in the other state. But now we have 3 states. We cannot use a formula similar to that to come up with a recursive formula, which was that probability of xn plus 1 being equal to 0 was expressed as probability of previous random variable being equal to 0, because the other random variable was shown as 1 minus the probability of that random variable not being in that state. So here we have 3 parts and we cannot simplify it any further, but it is clear that if you know probabilities of previous state, the previous random variable being in state 0, state 1 or state 2, and the 3 associated transition probabilities, you can certainly find the probability of next random variable being in this state of interest. Let's apply this formula to find the probability of x1 being in a certain state given the probabilities of capital X zeros, the initial probability distribution of capital X0 being in state 0, 1 or 2. Here you see that probability of x1 being equal to 0 is equal to summation of all these 3 parameters, 3 parts of the equation, and if you replace these with the initial probability distributions of pi 0 of 0, pi 0 of 1 and pi 0 of 2, you get this formula for probability of x1 being in state 0. You can find this random variable x1 to be in other states, say 1 or 2, by using similar argument and using the corresponding transition probabilities of from 0 to 1, 1 to 1, 2 to 1 and other probabilities. So if you know the initial probability distribution, which consists of pi 0 of 0, pi 0 of 1, pi 0 of 2 and the transition probabilities, you can find the probability of this Markov chain being in state 0, 1 or 2 when the first sampling instance occurs. If you know this, you can certainly use this as pi 1 of 0, pi 1 of 1, pi 1 of 2, and all these transition probabilities to find the probabilities of this Markov chain being in certain state at second sampling interval, and so on. If you look at these formulas, you should observe that they are similar to inner product of two vectors, pi 0, pi 0 of 1, pi 0 of 2, and these three transition probabilities. So all these formulas are multiplications of dot products of a 3 by 1 vectors. So all these transition probabilities and these initial probability distribution can be used to formulate this problem in a different format, in the format of vectors and matrices. Let's tabulate all these transition probabilities. Here that Markov chain is shown again along with a table of transition probabilities. This column represents the initial state of this Markov chain, and this top row represents the next state. So if this random variable goes from state 0 to 0, here is the transition probability. If it goes from state 2 to 1, here is the transition probability, and they are shown here. From 2 to 1, P is the transition probability, and from 0 to 0, 1 minus R is the transition probability. So this table of 3 by 3 represents all transition probabilities from 3 possible states of previous random variable to 3 possible states of next random variable, and they can be represented as a 3 by 3 matrix. This matrix is called P, and its name is transition matrix or state transition probability matrix. This represents one-step transition probabilities from different initial values of random variables to different next subsequent values of random variables. We can use this matrix P and the probability distribution vectors to find the probability distribution vectors of other random variables at other sampling instances. For example, if you want to find values of this vector pi 1 0, pi 1 1, pi 1 2 representing the probability distributions at first sampling instance, then you can find this as result of a multiplication of initial probability distribution vector pi 0 0, pi 0 1, pi 0 2 multiplied by this P, the matrix of transition probabilities. And if you want to find the probability distribution vector at second sampling interval, you can find it using the same probability matrix, transition matrix P, but using here the probability distribution at first sampling interval, pi 1 0, pi 1 1 and pi 1 2. But this vector is equal to this multiplication. If you replace this, you can see that the probability distribution of second random variable being in different states represented by pi 2 0, pi 2 1, pi 2 2 is equal to initial probability distribution times this matrix whole raised to power 2. This means you have to multiply this vector twice with this transition matrix, and this can be generally extended to come up with a formula that probability distribution at nth sampling instance is equal to initial probability distribution times p raised to power n, where p is this transition matrix, this probability transition matrix. We learned that if we have a more complicated Markov chain with more complicated transition scenarios, we can find the probability distribution at any sampling instance, nth sampling instance, from initial distribution before the Markov chain gets into action and the matrix representing all possible transitions from state to state, transitions in one instance, transition from xn to xn plus 1 or transition from x0 to x1. And you have to use the powers of this transition matrix. So if you want to find 7th probability distribution or probability distribution of 7th random variable capital X7, what's the probability that capital X7 is in 0 state, 1 state or 2 state? You can find that from initial distribution, the distribution of random variable capital X0 being in state 0, 1 or 2 multiplied by 7th power of transition matrix. It is simple procedure and you can certainly use that to solve for the probability values of capital Xn for different values n if you know the initial probability distribution and the transition matrix. Let's apply this procedure to the simple case that we have already solved in previous lecture, that is two-state Markov chain where device breaks down, comes to local facility and gets repaired the very next day always. Let's have a look at its different parts. This figure shows the Markov chain, the graphical representation of Markov chain. Here I have assigned numerical values to P. P was the probability that this will break down. I have assigned it a value of 0.1. The probability of getting this machine repaired in 1 day is 1. And the probability of this machine being in working state on 2 consecutive days is 0.9. So using all these transition probabilities, we have this transition matrix P where this is 0. The probability of this machine taking more than 1 day for getting repaired is 0. Here it is 1, and these are probabilities P and 1 minus P. Let's assume that initial distribution is 0, 1. That is, whenever you start this Markov chain, the device starts in the working condition. So initial distribution is always like this, that device is in working condition and then you start observing on day 1, day 2, day 3. Let's find the probability distribution on day 1. All you have to do is take this vector, put it here and multiply it with this transition matrix P. If you do that, you will get this vector of 0.1 and 0.9. So there is a 10% chance that on the first observed instance, the first day, device will be broken, and there is a 90% chance that device will be in working condition. Let's look at day 2. These are the probabilities 0.09 and 0.91. Day 3, 0.091, 0.909. Day 4, 0.0909, 0.9091. You can see that these values are converging. Somehow they don't change much. 0.9 remains and the change is only in the digits which are far away from this decimal, the digits which are not very significant. If you multiply this initial distribution with 100th power of this matrix, you will get the probability distribution of this Markov chain on 100th day. And those probabilities are shown here, which are same as the probability distribution on 4th day with 4 digits of accuracy. So what does this mean? This means that on 100th day, with this starting probability distribution, the probability distribution has settled down to this value. On 100th day, there is 9.09% probability that machine will be broken and 90.91% probability that machine will be in a working order. And the same probability will be applicable on 101st day, 110th day and 1000th day. I'm not saying that on 100th day or 1000th day machine will be broken or machine will be fixed. All I'm saying is that probabilities have settled down. Eventually, even though you started with probability of 0, 1, eventually the probabilities of finding machine in a working condition or in a broken down condition have settled down to their values of 0.0909 and 0.9091. Let's look at the values of capital P raised to power 100. This is the matrix that gets multiplied with initial distribution to give you the value of probability distribution on 100th day. If you change this 100 to 101, 102 or even 1000, this matrix does not change. So this matrix raised to a certain power, this has converged to this matrix. So we are again talking about convergence, and this convergence is element by element convergence. All the elements have converged to their respective values. Now look, if you want to find the probability distribution on 100th day, you will put your initial distribution vector here and multiply it with this column. So this row will get multiplied with this column to give you value of probability of this Markov chain being in state 0 on 100th day. Now think about these initial distributions. They are 0 and 1 here. They could be 0.5 and 0.5, 0.1 and 0.9, or 1 and 0. No matter what values you put, on 100th day you are going to multiply the two values with the same number. So this number multiplied by this is going to just give you this number. Similarly, no matter what the starting distribution, when you take this row and multiply it with this column, you are going to get this number because sum of these two numbers is 1. This is initial probability distribution. So this matrix P raised to power 100 or 1000, if it has converged to a final value, these columns represent the final settled down asymptotic probabilities of this Markov chain being in state 0 and state 1. So this transition matrix P and its convergence to a certain matrix and the values in this converged destination matrix give you a lot of information about the behavior, particularly asymptotic behavior of this particular Markov chain. We have started the usage of transition matrix capital P, its higher powers, and the values that these higher powers converge to, if they do converge, and the information contained in the higher powers of this transition matrix. The higher powers represents probabilities of transitions in multiple steps. The details you can see in your textbook, but the higher powers of this transition matrix P, if they converge, give you a beautiful collection of pieces of information. Let's apply these ideas to the more complicated device repair situation where device is initially sent to a local facility, and if it does not get repaired in one day, gets sent to some facility in other city or in other country. The state transition diagram is shown here with some numerical values. I have assumed that if device is working, it's in state 2, then with 90% probability it will be working again next morning, and with 10% probability it will not be working and will be sent to the local facility. Our local technicians are very good, and with 80% probability they usually repair the device and send it back the next day. And with 20% probability they fail, and that evening they send it out. Once it is in the external repair facility, they have a 40% probability of sending it back the next day and 60% probability of keeping it till next day. And once they keep it, they forget everything what they did the previous day, and on the next day they again have a 40% probability of successfully repairing it or 60% probability of not being able to repair it. Using all these numerical values, we find P, the transition matrix, the state transition probability matrix of this 3-state Markov chain. If you look at the second power of this P, it gives you this set of values. The third power of P gives you slightly different set of values. Fourth power again different values. And if you take 8th power, the values seems to be converging to a value. And if you take 32nd power of P, then these values have definitely converged, as all columns in the 32nd power of this transition matrix P have same values with 4 digits of accuracy. So somewhere between P raised to power 8 and P raised to power 32, the values have converged, and this converged matrix, this destination matrix, is very important because this tells you the asymptotic behavior of probability distributions. If you look at these particular values in this destination matrix to which these higher power matrices converge, they are 0.0435, 0.087 and 0.8696. We don't have to start with a particular initial distribution. No matter which initial distribution we start with, we are going to end up with these probabilities, and this is the probability of asymptotically this Markov chain being in state 0, that is, the device is at the external repair facility. So there is 4.35% probability that device is at external repair facility. Similarly, there is 8.7% probability that device is in the local repair facility, and there is 86.96% probability that this device is in working condition. So this P raised to power 32, which should be equal to P raised to power 100 or P raised to power 1000, tells you everything about the asymptotic probability distributions for this particular Markov chain. I hope you appreciate the use of this transition matrix and its higher power in analyzing the behavior of Markov chains. Let's apply this procedure to that example of an average Pakistani wishing and trying to go to perform Hajj. There we had a 4-state Markov chain, and I have assumed some numerical values based on my feelings about the whole system of applications being randomly selected to select the people who are going to go for Hajj. Let's have a look at that Markov chain and the associated transition matrix. This is the Markov chain. It has state 0, 1, 2, 3 as discussed in the last lecture. State 3 is where a person has performed Hajj and then he remains in this state. And state 0 is where he is thinking about applying, and there is a 90% probability that he will not apply. He will apply with a 10% probability, and once he has applied, his application will be selected with a 60% probability and will be rejected with a 40% probability. And once his application is accepted, there is a 99% chance that he will perform Hajj and only 1% chance that he will not, and his application will be considered again. From these transitions, you can get the transition matrix, and it has this simple 4x4 structure. Let's assume initial probability distribution of 1, 0, 0, where it means that when you start observing the person is in state 0, that he has not applied yet. This is natural choice, and if you multiply this with this transition matrix P, you get the probability distribution of first state. If you continue to multiply with this transition matrix P, you will get probability distribution of state 2, state 3 and state 7. If you look at state 7, there is still considerable probability that the person is still languishing in state 0, 63% probability, and only 25% probability that he has performed Hajj. If you continue this process and look at the 100th distribution, the distribution of 100th random variable, the state of this Markov chain at 100th observation time, then you see a nice property here that with 99.69% probability the person has performed Hajj. But there is still some non-zero probability that even after trying for so many times, he still has not performed Hajj. But this is certainly very close to 1, and person has a high probability of having performed Hajj if he continues to try and this Markov chain reaches its 100th sampling time. In real life in Pakistan, situation is not that bad and you don't have to let this Markov chain go on for 100 transitions. The reason is that Government of Pakistan says if a person applies for 3 consecutive years and his application is not selected, in 4th year his application is not put into that random draw process and his application is selected definitely. So all a person has to do is be persistent, apply for 3 consecutive years, and even if he does not succeed in 3 tries, the 4th try is definite, a sure thing. This new situation can also be modeled by a Markov chain where you count the number of failures, and once you have reached 3, next time you definitely succeed and the Markov chain ends there. In today's lecture, we analyzed in greater detail a few Markov chains. We started with simple 2-state Markov chain and moved on through different examples with 3 and 4 states. We learned the use of transition matrix P, its higher powers, its convergence, and how it can be used to make assertions about asymptotic behavior of Markov chains. In next lecture, we are going to continue with this treatment of Markov chains through the transition matrix, and we are going to look at certain characteristics of certain states of Markov chains. Till then, I wish you the best. Thank you. Khuda Hafiz.